Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Welcome. This is Mr. Simon, and we are here to use chemistry to change our world. We are still on unit number 12, conductivity of solutions, and today we are actually going to talk about determining solubility product using molar conductivity. So maybe the first thing we're going to note about this topic is that we are introducing solubility product. If we talk about solubility, this time we shall refer to it as concentration in moles per liter, or we can also talk about concentration in grams per liter. Then we shall look at the definition of solubility product. So this is what we are going to be talking about today. So meaning if you're given molar conductivity, you can be able to determine the concentration, then after determine the solubility product. So by the end of this lesson, students should be able to determine the solubility product using molar conductivity. So that's the lesson's objective. So quickly, let's go and talk about the definition of solubility product. Is a product of concentration of ions raised to appropriate powers in a saturated solution of a sparingly soluble salt. So as we've said today, we are going to use molar conductivity to determine the solubility products. So we are going to look at examples, but before we talk about these examples, let's go back to our definition of solubility product. So here we are going to call solubility product we are going to refer to it as KSP. So if you look at our definition, we have said is a product of concentration of ions raised to appropriate what? Powers in a saturated solution of a sparingly soluble salt. So solubility product, normally we use it to determined when we have a sparingly soluble salt. So what is a sparingly soluble salt? Is a salt which partially dissolves in what? In water. Like for example, we can take an example of lead 2 chloride. Lead 2 chloride is sparingly soluble in what? In water. Lead 2 sulfate, you know from qualitative analysis of senior 4, that this, when you react lead 2 ions and chloride ions, you get a white precipitate of lead 2 chloride. So we can say it is sparingly soluble in what? In water. So we can also have barium sulfate, reacting sulfate ions and the barium. Then you can also have hydroxides. So again, in our definition, we have also what we call a saturated solution. So someone may ask, what is a saturated solution? What is a saturated what? Solution. So a saturated solution is a solution which can dissolve normal solute at a given what? Temperature. So this is what we look at here. So meaning our solubility product is supposed to occur at constant what? Temperature. So for example, here you can say, if you're writing equations for solubility product, we get our solid. This one, we dissolve it in water. We are going to use AQ as aqua. Then we have lead 2 plus and then 2 chloride what? And so that's the equation for solubility. Equation for what? Solubility. So we have also here, we have lead 2 ions, aqueous. This is aqueous, but here we say we dissolve in water. So partially dissolves. So meaning that we have lead 2. We can have, we have sulfate here. This is sulfate. Sulfate 2 minus, then aqueous. Yeah. Then we also have barium. Barium, aqueous, barium 2 plus aqueous plus also sulfate. Yeah. So these are equations for solubility. Then we go to the for the statement of KSP. So we are going to say that here that our solubility product KSP, if we consider the first equation, can say consider first what? Equation. This is our equation 1, equation 2, and equation what? 3. The third. So the second and the third are almost similar. So we are going to write the equation, the KSP expression for the first one. So it will be normally the product of ions. So this is an equilibrium constant, and we don't normally include the solid substances. So this is why we have only products. Then again, from our definition, then again, if we have 2 here, we also put 2 squared. If we have 1, we just leave it as it is. Like for example, if you look at our second equation, where we have KSP. So KSP, we can say we have lead 2 plus, and then also the sulfate. So this is what we have. Those are the equations for our. So here we can say we have written the equation for solubility of lead 2 chloride and the expression for KSP. Expression for what? KSP. You can also take another example. Is there, you can say consider if we have, for example, silver carbonate. So here we have 2 silver carbonate. Yeah. If we have silver carbonate, so if you write the equation for solubility of silver carbonate, will be this one. So we have, supposed to have a 2 here from carbonate. So we shall have silver plus aqueous. That's also the carbonate, which is aqueous. So we shall have our KSP value will equal to concentration of silver ions squared and the carbonate 2 minus, like good. Yes. So you see, even here we have put squared. So it's good for us to represent that we have dissolved it in water. So these are expression for KSP expressions. So from there, we are going to go back to our topic, which says that using solubility, using molar conductivity to determine solubility. So we are going to determine solubility in moles per liter, which is going to be concentration. So as I've said, when we say the word solubility, we can mean concentration in moles per liter. Moles per what? A decimeter. Then solubility, we can also have concentration in grams per decimeter cube. So this is molarity and this is mass concentration. So we can have solubility in moles per decimeter. We can have solubility in grams per what? Per decimeter. So borrowing our knowledge of mole concept, we can use the same solubility in moles per decimeter, which is a molarity. Solubility in grams per decimeter cubed, which is our mass concentration, or we can call it concentration in grams per what? Per liter. So let's go back briefly. For example, here, this is the equation for solubility or dissolving of our sodium carbonate. It is silver carbonate in water. So we know that silver carbonate is sparing soluble in what? In water. Because it is sparing soluble in water, we represent it with these equations. If you remember when we talked about weak electrolytes. Weak what? Electrolytes. So if an electrolyte is weak, it will also spare we said it will not dissolve completely in water. doesn't dissociate completely in what? In water. Even this one does not dissolve completely in what? In water. That's why we have here and we have also that one. Then now let's go to our number 2 of the question. So the question says that the conductivity of a saturated solution of sparing soluble salt MX in water is that one. So they have given us the conductivity, and the molar conductivity of MX at infinite dilution is given as 138.3 times 10 to the power negative 4 Siemens meter squared per what? Per mole. And the question is asking us to calculate the solubility in moles per decimeter cubed and the solubility product. So quickly, we go and say, we try to note what is given. What is what? Given. So what is given is K. They have given us K, which is 1.88 times 10 to the power negative what? 4 Siemens per what? Per meter. Then we have also molar what? Conductivity at a given what? Concentration. Okay, it's actually 0 concentration. Is molar conductivity at 0 concentration is 138.3 times 10 to the power negative 4 Siemens meter squared per what? Per mole. So these are the two things we have. So we can use these two things to get our solubility, which we are going to call C, which is going to be, again, molarity. By saying that molar conductivity at any concentration is equal to K over what? C. So because we have our units in meters, we said here we divide by 1,000. Then we have C. We are going to say C, this is what we want, will equal to K over molar conductivity, this time at 0 concentration times what? 1,000. So we get our K. K will be 1.88 times 10 to the power negative what? 4. Divided by 138.3 times 10 to the power negative what? 4. So we cancel this and cancel that. Then we divide. So we shall be able to get our C. So we are going to say value is 1.8 divided by 138.3. So our C will be 0.0135 what? 9 molarity. Yeah, that is our C. So we have got our C. So the next step is this C will be our solubility. Let's call it S. Supposing our solubility is S, we are going to call this one our solubility. So we continue to our next part of the question. Next part of the question, which tells us to calculate the solubility product. For us to be able to get solubility product, what we normally do, we say mx, m what? X, which is going to be a solid partially dissolves in what? In water. Then we have here aqueous, we have mx, m, that's, yeah, let's say like that because they are unknown. So supposing we have a charge of positive 1, again we shall have this. So that is our equation for solubility. Then I want you to note, if you want to get solubility product, we say if this is S, this will be S using mole ratios, and that will be what? S. Then we say, but KSP, we have said, is the product of concentration of the what? Ions. Product of concentration of what? Ions. So because it's product of concentration of ions, we now say, but each concentration we have seen is SS. It's good for us to put this. So S times what? S. So S KSP is equal to S squared. But we said our S is equal to 0.01359. So here we shall put 0.01359. Yeah, but I think we forgot something here. because we're supposed to have 1,000. Supposed to have 1,000. So if it is 1,000, meaning here we shall multiply times 10 to the power negative what? 3. So here, again, we shall have times 10 to the power negative what? 3. So we do like this, then we square. And we what? We square. So we're going to divide by 1,000, our answer, and after we square. Yeah. So our KSP value will equal to 1.8478 what? 87. Let's stop there. So units will be mole squared. Because here we have molar squared, even there will be molar squared. So we have 1.88 divided by 138.3 divided by 1,000, yeah, and squared. So that's going to be our answer. So that's how we find solubility what? Product. So let's look at another example. So this time our example they have given us the molar conductivities of different compounds, and they want us to find the molar conductivity of silver what? Chloride at infinite dilution. Then they said if the electrolytic conductivity of saturated aqueous solution of silver is that one, then at 298 Kelvin is 3.41 times 10 to the power negative 6 Siemens per centimeter. And that of pure water is 1.6 times 10 to the power negative 6 Siemens per centimeter. Calculate the electrolytic conductivity of silver. Right, that one is new also, we are going to look at it. Then they say calculate the solubility of silver chloride in moles per decimeter cubed and gram per decimeter what? Cubed. Then the solubility product of silver chloride. So we are going to do that one also very, very quickly. So in our previous lesson, we had seen how to get the molar conductivity of different compounds if they have given you molar conductivity of some compounds. So we can borrow that idea of Corach's law of infinite what? Dilution. Like for example here, we are on question number 3. Question number what? Number 3. So we have silver. We want molar conductivity at infinite dilution of silver chloride. So question number 1A, actually question number 3A will equal to, so we look at in our compounds, we have silver nitrate, silver what? Nitrate. So it will give us silver nitrate to give us silver. Then we have also molar conductivity of KCl minus molar conductivity of potassium what? Nitrate. Yes. So meaning we have this, we are going to cancel that one with that one, then we shall remain with that silver what? Chloride. So we continue and we substitute. So we are going to say 145 plus 149.9 minus 133.4. So let's calculate very quickly. So we're going to say 145 plus 149.9 minus 133.4. Point what? 0.4, yeah. So our answer is 161.5. So it is very good to check our answers. 145 plus 149.9 minus 133.4. Because our question is continuous. So if you make a mistake on the first question, it means everything becomes wrong. So we say per mole. Then from there, now they have given us, on part B, they have given us 2 types of Ks. So, but they want to get the K for silver chloride. So we can say K for silver what? Chloride. This is also somehow new, equal to K for silver chloride, silver chloride saturated solution minus K for silver for water, K for water. So someone may say these are the same, but this one is the one we are going to use in our calculation. But we get it by subtracting when we have a saturated what? Solution from the definition of solubility product. So we have 3.41 times 10 to the power negative 6 minus 1.6 times 10 to the power negative what? 6. So 3.41 minus 1.6, which is equal to 1.81 times 10 to the power negative 6 per ohm centimeter squared per watt per mole. Yeah. So that is our answer. So now we got to go to our solubility product like we have done here. But before we go to solubility product, it's good for us to find our solubility. So this is going to be our solubility, C. So C will equal to, as we have seen here, it will equal to K over molar conductivity, which we have here already. But this time we are going to multiply times 1,000 because we have units in centimeters. So we continue here, then we say we have our K 1.81 times 10 to the power negative 6 divided by 161.5 times 1,000. Let me not forget this 1,000 this time. So we have it divided by 161.5. So we can say 1.81 divided by 161.5. So you can try out and see if you can get the same answer, times 10 to the power negative 6. So this is physical chemistry. So that's why we are always calculating. We are always what? Calculating. So our C, which is our solubility, is going to be 1.12074. And write many decimal places times 10 to the power negative 5. We are going to say mole. So that's our molarity. So now we want to get solubility in grams per liter. Grams per what? Per liter. So let's do it here. So we are going to say that you know that number of moles is equal to mass over molar mass. So it means that our molarity will equal to this one, which we are going to call our concentration in gram per liter. Gram per what? Per liter. Divided by molar mass. So this concentration in gram per liter will be our solubility in gram per liter. So equal to molarity times molar mass. Times molar mass. So our molarity will be, we have got to 1.12 times 10 to the power negative 5 times molar mass of silver 108 plus 35.5. So we say times 108 plus 35.5. So you try out the calculations and see if you are getting the same answers. 0.883 times 3 gram per decimeter. So this is our solubility. Solubility in gram per decimeter cubed. That is our solubility. But we have forgotten to multiply let's multiply with our powers there. So thank you very much for reminding me. We've forgotten to multiply. So it's supposed to be times 10 to the power negative 3 gram per decimeter cubed. Then after we go to determine, let's go to determine our solubility product. Solubility product. So solubility product is what we want, KSP. So how do we get it? We first say silver chloride solid in the presence of water will give us silver ion and the chloride ion. So aqueous. So we say if this is S, this will be S and this will be S. That is molarity. So KSP will equal to this one and that one. So our KSP will be S times S, which is S what? Squared. So will equal to 1.1200743 times 10 to the power negative what? Negative 5 squared. So it will give us our solubility what? Product. So our answer will be 1.256 times 10 to the power negative what? 10. So that is our KSP. That is our KSP. So KSP values, those are our KSP what? Values. So I'm going to leave you with one question. Actually, there are two. One is write the expression of solubility, which is this one. Expression of solubility. This one, the equation, and then the expression of solubility product of calcium phosphate, lead 2 chromate, and magnesium hydroxide. So I think you can try out that. Then here we have also another question, say the specific conductance of a saturated solution of barium sulfate is that one, and that of water is that one. So you can follow as we have done here. This time they have given us two types of Ks. That is the specific conductance. And they've given us the ionic conductivity of barium and sulfate. And meaning if you want to get the ionic conductivity at infinite dilution, you need to add both of those ones. Then you use them to get the, like for example, the question is asking, calculate the specific conductance of barium sulfate. So you can get the K. You can get the what? The K. Then calculate the molar conductivity of barium sulfate. That is, you add the conductivity of the what? Of the ions. Then you find the solubility. You find the solubility and then you find the solubility product. Thank you very much for following me today. Hope you can be able to use molar conductivity, and molar conductivity is at infinite dilution to find the solubility product. God bless you very much. We shall meet next time.